Welcome to learning Program 10.3a on the IBM Selectric Typewriter. This program covers the input section of the Selectric Typewriter. As a general introductory statement, let us simply say that the input section of the typewriter consists essentially of the keyboard and a series of interposers and links, which either directly or indirectly have the ability to control the horizontal movement of selector latches. IBM calls some selector latches operational latches because they are used to select operations other than printing operations. The mechanisms related to the vertical motion of the selector latches and operational latches are covered by Learning Program Series 10.2 and 10.4. Any vertical movement of a selector latch is part of the output section or output mechanism in the Selectric Typewriter. For ease of explanation, we will divide the study of the keyboard or the input section into two segments. Segment A, Theory of Operation and Adjustments of Printing Operations. Segment B, Theory of Operation and Adjustments of Non-Printing Operations. In this picture, all of the keys which cause character printing have been hidden under the paper. If you now survey the functions which are not covered, the non-printing functions, you find that there are barely a handful of them. If in addition you consider that all the keys covered by the paper function essentially the same way, and that when you study one of them you have, with the exception of the repeat keys, studied them all, the whole project of studying the input section of the IBM Selectric Typewriter becomes very easy to oversee. In previous training programs, we have already seen that tab set and tab clear operations, the margin release operations, as well as tabulation engagement, are very simple manual functions, meaning that they do not require any positive nor negative power in order to be carried out. They depend entirely on the effort or force supplied by the operator in order to function. Whenever an operator uses the somewhat more sophisticated non-manual input mechanisms, two major occurrences will take place in the machine. 1, the choosing of the selector latch or latches, and 2, the choosing of a source of power to drive the selected latches. First, we shall study Segment A, covering the input to character printing operations. Segment B, covering the input to non-character printing operations, will be covered later. For the purposes of being able to repair the Selectric Typewriter, you must be able to recognize that the input section has the job of choosing a latch or latches, and that of picking a source of power to drive the chosen latches. In a negative power system, a selected latch is a part which moves out of the way of the cam follower, so that under spring tension, the blue pencil, the cam follower, at the yellow pencil, can move or rotate into the dwell of the cam. The resulting motion of the cam follower is then used to operate some output mechanism. In this case, it is used to select a low-velocity cam for the printing operation. The point at which the selected latch releases the cam follower is located exactly behind the strong driving spring indicated by the blue pencil. Furthermore, in negative mechanisms such as this one, the cams are used to restore the spring tension, which provides the power to drive the mechanism. To make this section of the typewriter easier to understand, let us first clarify the sequence of events which takes place every time the Selectric Typewriter engages in a printing operation. Items 1 and 2, the presetting and the carrying out of the latch selection, are studied as part of the input section of the Selectric Typewriter. Item number 3, the performing of the character selection, involves vertical motion of the latches. This is covered in Learning Program 10.4b. It represents an output function. Item number 4, the actual printing of the selected character, is covered in Learning Program 10.4a. Item number 5, the restoring of all the parts, is always studied together with the operation of the parts. What we need to remember from all this is that first, the machine presets the latch selection and chooses the source of power. Second, it performs the latch selection. Third, it performs the character selection. Fourth, it prints the character. Fifth, it restores all the parts. When it comes to the keyboard, it is most advantageous to use drawings such as this one. The parts in this illustration enable us to explain how the presetting of the latch selection is accomplished. When the key top is depressed, it pivots the keylever, shown in blue, at the rear. And with the keylever pawl, it in turn pivots the character interposer, shown in yellow, at the front of the keyboard. For each character on the keyboard, there is one character interposer, and the interposers are all different from each other. Thus, if we have 44 character keylevers, we also have 44 character interposers. Once the rear of the interposer is depressed, the interposer latch spring locks the interposer into its low or set position as illustrated. Actually, this is all there is to the presetting of the latch selection. It is important to note that only one interposer can be depressed at any one time. To prevent simultaneous depression of more than one interposer, the manufacturer has installed a device called the Compensator tube. We shall examine the Compensator tube a bit later. The second part of Step 1 is the tapping of a source of power for the character printing operations. The depression of the interposer also causes the lowering of the cycle bail, and the subsequent releasing of the cycle clutch latch link and pawl from the cycle clutch keeper. As we studied in Program 10.1b, before moving on, you should attempt to find these parts on your machine. You can find them even without our help. Be sure to also learn all the new names of the parts. By tilting the machine on its back by about 120 degrees, you will be able to locate the indicated character interposer latch springs and observe a latch-down interposer, as shown here. As mentioned, the latching down of the interposer is really all there is to the presetting of the latch selection. If you happen to encounter any difficulty in depressing a keylever, don't let it disturb you at this point. Simply continue this program. Shortly, we will start explaining the ways in which the keyboard may turn up locked. When an interposer is latched down, it places a step in front of the filter shaft, so that the filter shaft can push the interposer towards the front at the time when the filter shaft is rotated top to the front by the cycle clutch. Caution! If we inadvertently turn the filter shaft top to the rear, the small interposer latch spring will sustain damage. It is therefore very important that no matter what work we are performing on the typewriter, the filter shaft must always be turned top to the front. This is the same rule which applies to the hand cycle wheel on the operational shaft. The position of the filter shaft could actually lock the keyboard. If the filter shaft happens to be rotated too far top to the front, it can interfere with the depression of the interposer. If this happened in the field, the operator would probably call because of an occasionally very hard keyboard, or simply because of a plain locked keyboard. As you start working with the input section, it is necessary for you to be aware of all mechanisms which have the ability to lock the keyboard. This is just one of them. Can you still remember which mechanism or adjustment prevents the filter shaft from turning too far top to the front? Take a moment if you need time to decide. The cycle clutch overthrow stop adjustment is the correct answer. The indicated clearance should be only 0.25 millimeters. Since it seems rather large in this picture, can you tell us how we check this clearance? Take a moment to decide on the correct answer. You are correct if you answered that we check the cycle clutch overthrow, or, for that matter, the whole printing mechanism overthrow clearance, by first rotating the cycle shaft until it finds its check pawl position. Only then can we check the overthrow play for the printing mechanism, and the play should be 1/4 of 1 millimeter. If you said the cycle clutch overthrow stop adjustment, you nailed it. That little stop holds the filter shaft to just 0.25 millimeters of overthrow, and when it's off, the operator feels it as a hard or completely locked keyboard. Here's the trick. Rotate the cycle shaft until it finds its check pawl position first. Only then can you measure the overthrow play of the printing mechanism, and it should come out to exactly 1/4 of 1 millimeter. We mentioned the compensator tube before. It consists of a tube which has numerous slots and steel balls inside of it. The job of the compensator tube is to allow the depression and latching of only one interposer at any one time. Very rarely will you have to take the compensator tube out of the machine. And since this side of the compensator tube is mounted against the cast frame of the keyboard, this view of the compensator tube is rarely, if ever, seen by the average Selectric serviceman. The compensator tube assembly is held together by 4 clamps and 4 screws. On the lower side of the screws, the clamps hold the compensator tube. And above the screws, the clamps hold the dust shield, or plate, which, besides strengthening the assembly structure, protects the slots in the compensator tube from any foreign matter. Finally, notice the plate under the tube, which also has slots in it. It is called the rear interposer guide comb. This is the lower portion of the rear interposer guide comb. On an assembled machine, you can also see the lower portion of the compensator tube by looking through the spaces between the interposers. Be sure to take a good look at all this. Examine also the plugs at the ends of the compensator tube, holding the steel balls inside the tube. Besides holding the steel balls inside the compensator tube, these plugs are also responsible for the rather fine adjustment of the clearance between the steel spheres inside the tube. In this drawing, we can clearly see the upper portion of the character interposer, which will engage with a slot of the compensator tube when the interposer is depressed. One of the steel balls inside the compensator tube is shown in the drawing. Whenever one character interposer is depressed, the compensator tube balls have to move out of the way of the upper lug of the interposer so that it can lodge itself between the balls. The compensator tube balls are slightly wider in diameter than the distance between the character interposers, so that it is impossible to depress 2 adjacent character interposers at the same time. This is illustrated in the upper figure. Furthermore, the clearance between the steel balls is adjusted so that there is only enough room for one character interposer to be lodged between the balls. Notice in the figure at the bottom that all of the excess space between the spheres has been taken up due to the depression of only one character interposer. Any depression of another keylever is thus stopped, making the keyboard appear to be locked. What can we do when a character interposer is latched down and we really do not want it down? One option is to simply cycle the typewriter through a print operation, and the interposer will be restored at the end of the operation. We will see in detail how this is done shortly. Another option is illustrated here. With the aid of a screwdriver, we can push the individual interposer towards the front of the machine, in the same way the filter shaft does it. Be careful to exert only rear-to-front force on the interposer, so as not to strain the interposer latch spring. The interposer will thus come out of engagement with the compensator tube and also out of its latch-down position. In short, it will return to its rest position under the action of its own restoring spring after we cause it to become disengaged from the interposer latch spring. Another possible lock for the character keys on the keyboard is the on-off switch. The green pencil points at a link which holds the on-off key in its position. With the movement of the link pointed out by the yellow pencil, we are able to rotate the clamp fastened to a bail called the keyboard lock bail, indicated by the blue pencil. Notice that when you turn the on-off switch to on, the lockout bail turns top towards the front. Let us now return to a drawing to enable us to see it all in one frame. When the switch is turned off, it is depressed at the point marked 0, and the switch lever rotates counterclockwise. This motion will turn the lockout bail clockwise. Clockwise rotation of the lockout bail will pull downwards through the intermediate tension spring on the keyboard lockout bell crank, colored green. Lockout bell crank is not a good name for this part, since it really is only a plain lever and not a bell crank at all. In fact, it bears quite a resemblance to the character interposers. It is a dummy interposer at best, or a lockout interposer. When the on-off switch is turned to off, this keyboard lockout interposer is pulled into the compensator tube and locks out all of the character interposers, as we have seen earlier. One final comment. When the switch is in the off position, the lockout bail positions itself under a downward-reaching extension of the cycle clutch latch pawl. This enables the bail to also prevent the engagement of the cycle clutch. Very simply, then, do not expect to be able to depress an interposer or hand cycle a printing operation when the on-off switch is in the off position. Finally, we must make you aware of the possibility of the carrier having reached the right margin, as is pointed out here by the red pencil. Through the bell ringer bail and the arm, or paddle, which is connected to the bail at the point indicated by the yellow pencil. This position of the carrier will lock out all the character interposers by pushing down the same lockout interposer, which we studied in connection with the on-off switch. What then do we do to enable us to depress a character if we happen to run into this condition? We simply depress the margin release key, as we have seen in earlier learning programs. Since all of the character keys are depressed for the same purpose, namely printing, it does not surprise us to find that all of the character keys will also use the same clutch. This clutch, while it is called the cycle clutch, really is the print clutch, and it actually performs only 1/2 of one revolution for each character printing operation. When the character interposer is depressed, the indicated center lug will press down the bail immediately below it, namely the cycle bail. To continue, let us look at a cross-section of the keyboard. As mentioned, with the center lug or the wide lug on the character interposer, the operator pushes down on the cycle bail. The cycle bail, in turn, will press down on the cycle clutch latch pawl, the yellow pointer, causing it to rotate counterclockwise, and thus to disengage from the cycle clutch keeper, shown in red. This allows the cycle clutch link to move towards the front of the typewriter. Eventually, at the end of the resulting printing operation, the restoring of the link is performed positively by the action of the restoring cam and restoring stud, indicated by the red pointer. Take whatever time you need to learn any new names of parts. It is the action of this spring, connected to the cycle clutch latch link, which causes the cycle clutch latch to disengage the cycle clutch. Once the cycle clutch sleeve is free to rotate, the clutch closes and turns the cycle shaft, as was explained in Training Program 10.1b on the positive power in the Selectric Typewriter. When the cycle shaft turns, so does the filter shaft, and the turning of the filter shaft top to the front causes the interposer to move towards the front of the machine. In the process, we carry out step number 2, which is latch selection. Let us now investigate how the latch selection is accomplished. Notice that the lugs under the interposer have the ability to push the selector bails towards the front whenever the interposer is pushed forward. Each selector bail has its own latch interposer. Notice also that the vertical lug on the latch interposer is positioned in such a way that whenever the selector bail is moved towards the front of the machine, the corresponding latch interposer is moved forward also. Actually, the bails are pushed to the front by the interposer only if the chosen interposer happens to have one of the vertical lugs pointing downward behind the bail. Although each keylever has an interposer, the interposers are all different from each other. They differ by the number and the position of these vertical lugs. This enables each interposer to choose its own combination of selector bails to push forward. The interposer in this drawing has only one lug. For each of the indicated cavities, there is a selector bail. An exception applies to American machines. They do not have the rearmost selector bail, which in this picture goes into the right end cavity. Every latch interposer, yellow pointer, is in turn connected to a latch, red pointer, which will be pulled toward the front and away from the latch bail when the latch interposer is pulled toward the front. We can summarize this by looking at it backwards. Each latch has its own link, its own latch interposer, and its own bail. During the rotation of the cycle shaft, the positive latch bail, red and green pencils, goes through one oscillation, first down and then back up again. The selector latches that remain under it are all pulled down by it, so they are all positive latches. During a particular printing operation, those latches which have been pulled forward by the lugs on the interposer are latches which, for the upcoming character print operation, are not used by the output mechanism. This means they have literally been filtered out. Only the latches that remain under the bail are the selected latches. They will be pulled down by the cycle bail, and they will be used to perform the character selection. This whole procedure is called negative logic or reverse logic. For the -5 bail, however, indicated by the yellow pencil, the operation is quite different. In the case of the -5 mechanism, we have a negatively powered output mechanism. The latch, red pencil, which is pulled toward the front of the machine, releases or gets out of the way of the cam follower, yellow pencil, in order to allow the selected operation to take place. We say in this case that the machine uses positive logic because we pull forward a given latch in order to operate the mechanism to which that latch belongs. On the type element, we see that in order to print the correct character, we must be able to turn the element by measured increments in a horizontal or nearly horizontal plane and also in a vertical plane. To make a long story short, the element has a total of 88 different characters, arranged in two hemispheres. One half of the element has all the capital characters, the left side in this picture, and the other half has all of the small letters. The rotation of 180 degrees needed to select between the two hemispheres is the part of the rotate mechanism that IBM calls the shift mechanism. With the shift mechanism, we cut the total number of characters from which we must choose down to 44. You will also notice that in the vertical direction there are 4 rows or belts of characters. With the tilt mechanism, we can choose any one of these 4, cutting the number of characters to choose from down to 11. Of these 11 characters, one does not require any rotation because it is already in the correct position to print. When the tilt is 0, this character is a Z. You can check this on any properly adjusted machine. You will notice that when the element is at rest, it is already in the proper position to print a Z without the need for any further rotation. This cuts the number of characters requiring rotation to a total of 10. Here we are looking at the element as seen from the rear of the machine, with the shift mechanism set to print small characters. Notice the position of the Z in this picture, and then the T under the Z in order to print the T. All we would have to do is tilt the element by 1 tilt increment. By counting the letters to the right of the small letter T, we find 5 more small characters. The same is true for the left side of the letter T. There are 5 more small characters to the left of T in order to select any of the 10 characters located to the left and right of the letter Z, T, the exclamation mark, or J. We use the portions of the rotate mechanism called the positive 5 rotate mechanism and the negative 5 rotate mechanism. The mechanisms indicated here are used to perform character selection. They are part of the output section of the Selectric typewriter. The yellow pencil indicates a point in the tilt differential, and the red pencil indicates a point in the rotate differential. The tilt mechanism, or tilt differential, is capable of turning the element in a vertical plane by increments that vary from 0 to 3. With this tilt mechanism, we can select any of the belts around the type element. The rotate differential is capable of turning the element within any of the tilt planes up to 5 rotate increments in the counterclockwise, or positive, direction, and up to 5 rotate increments in the negative, or clockwise, direction. If you trace these two mechanisms downward, you will find a series of latches. By pulling some or most of these latches down, we obtain various amounts of tilt motion and positive rotate motion. The job of the input section of the Selectric typewriter is either to filter out the latches which should not be pulled down during printing, or to disengage those latches which hold the negative-powered, spring-loaded mechanisms in their rest positions. Let us now do a bit of reviewing. It is up to the Interposer, red pencil, to select or filter out latches, and thus determine which mechanism to use. Through the proper latch selection, the machine determines just how much tilt motion or rotate motion should be used to position the element so that it produces the character depressed by the operator. The interposer is just what the name implies. It is positioned between the operator, or keylever, green color, and the output mechanism of the typewriter. The lugs at the bottom of the interposers are used to push selector bales toward the front of the machine. The selector bales, in turn, pull the latches which should be filtered out or excluded from the particular print operation. Take a good look at the interposer lugs from underneath the keyboard and convince yourself that there is only one interposer of a kind. Interposers differ from one another by the quantity of these lugs and their relative positions. As mentioned earlier, the indicated cavities are occupied by selector bales, and as you know, there is one selector bale for each selector latch. Depressing the key lets us latch down a character interposer, yellow, and thus preset the latch selection or latch filtering. When the interposer was depressed, the white center lug on the interposer depressed the cycle bale and thus released the cycle clutch latch link, which ends up engaging the cycle clutch. The engagement of the cycle clutch provides the power we need to drive the printing operation, so we have selected a source of power. Now the clutch can drive the filter shaft, and when the latch-down interposer is pushed toward the front, wherever there is a lug behind a selector bale, that bale will also be pushed toward the front. Whenever a bale is pushed toward the front, a latch is pulled toward the front. That is how the machine performs latch selection. Notice that this interposer comes equipped with all of its lugs underneath it. Not a single one is missing. This means that all positive selector latches and the -5 selector latch are going to be pulled forward. When all positive latches are pulled toward the front, there will not be any tilt or any positive rotate motion prior to the printing operation. However, since the -5 latch is also pulled toward the front, we release 5 increments of negative rotation for the type element. If we actually perform this on the machine, it turns out that the number 1, or the bracket, would print, since it needs this particular selection in order to be placed into the correct position for printing. That is how the machine performs character selection. Before you continue, be sure that you can explain the operation of this section of the input mechanism. Do not hesitate to review this material while you check out these statements on your machine. As the filter shaft pushes the interposer toward the front, the interposer latch spring gradually loses hold of the tail end of the interposer, so that it can again be restored by the spring located above it. The restoring force for the interposer is at once upward and toward the rear of the machine. All we have to do to see it happen is to rotate the filter shaft far enough, preferably using the hand cycle wheel and the cycle clutch to drive it. Toward the end of the print operation, the cycle clutch restoring cam, through the stud indicated by the red pointer, restores the cycle clutch latch link, so that the cycle clutch latch pawl can again reset itself behind the keeper at the point indicated by the yellow pointer. Due to the speed at which the machine functions when the motor carries out the operation, it is very common for a keylever to still be down when the interposer restores. What happens in such instances is shown quite clearly in this drawing. The keylever pawl is temporarily rotated out of the way of the restoring interposer. Only after the operator has allowed the keylever to be restored by the keylever spring can the deflected keylever pawl reset itself above the upper lug of the interposer. The spring which restores the keylever pawl on your machine may well be a leaf spring placed on top of the keylever, instead of the small coil spring shown here. The bottom of the slots in the keylever guide comb provides the lower stop, or limit, for the depression of the keylever, while the upper stop, consisting of a rubber-covered rod, is held in position by the tongs of the same guide comb. There are 4 rows of keytops, which are mounted on keylevers of the same length at different distances from the pivot point of the keyboard. On the part of the operator, this requires different amounts of force to depress the keylevers of different rows. As we mentioned earlier, one of the most critical factors affecting the success of the serviceman is satisfying the operator when it comes to the touch of the keyboard. To equalize the amount of finger pressure the operator has to produce to depress keylevers of different rows, IBM has provided auxiliary keylever restoring springs, which are simply placed under the regular keylever restoring springs. When a keylever has its keytop right next to the spacebar, its mechanical advantage is greater than that of the keylevers further to the rear of the keyboard. As a result, the keylever closest to the spacebar gets the longest and most effective auxiliary keylever restoring spring, indicated by the blue pencil. Keylevers with keytops in the second row, front to rear, receive the medium-sized auxiliary keylever restoring spring, indicated by the yellow pencil. Keylevers from the third and fourth rows, front to rear, both use the size of auxiliary keylever restoring spring shown by the green pencil. The majority of the characters are all printed with the same amount of momentum when the type element hits the paper. Some symbols, however, cover only a very small surface of the written page, and they would cut through the paper unless they are made to print with less momentum than the average character. To solve this, the machine comes equipped with a low-velocity selection mechanism. By reducing the velocity of the element during the printing operation, the resulting momentum is also reduced. All characters using this mechanism are called low-velocity characters. Once again, the interposer performs the selection between a sharp, fast-rising cam for high-velocity printing and a more rounded cam for low-velocity printing. Detailed discussion of this subject is given in Program 10.4a when the interposer is pushed forward by the filter shaft. It meets the lug on the low-velocity vane, rotating its top to the front. In connection with the input to printing operations so far, we have covered the theory of operation of a total of 6 selector latches. We will now study the 7th latch, which has the ability to release the velocity control cam follower at the point indicated by the red pencil. Let us take this in small steps. We mentioned this mechanism earlier as an example of a mechanism driven by negative power or spring action. In its controls, this mechanism may look a lot different from the -5 rotate mechanism, but it works in exactly the same way. The velocity control cam follower, green pencil, must be allowed to select a low printing velocity for characters with a small printing surface or area. During any printing cycle, the cam is made to turn with the filter shaft, but before the cam follower can follow the cam, the input section must select low velocity printing for that particular printing operation. Only symbols such as the period, the comma, the underscore, and a few others use this low velocity selection mechanism. The signal from the input section to the low velocity mechanism is transmitted through the link indicated by the yellow pencil, and it comes in the form of a pull toward the front, just as with the other selector latches. In the process, the low velocity control cam follower is released, or unlatched, at the point indicated by the red pencil. During the printing operation, the now unlatched cam follower follows the contour of the low velocity mechanism, restoring cam, indicated by the green pencil. If you look at the lowest end of this cam follower, you will find the low velocity control cable hooked up to it. The cam follower will pull this low velocity control cable during the print cycle. This low velocity cam follower is now free to follow the cam during the print operation. It will do this under the action of the spring indicated by the red wedge, so the operation is negatively powered. At the bottom of the low velocity cam follower, where we find one end of the low velocity control cable, the cable is pulled toward the front of the machine. The other end of the cable, fastened under the carrier, will be pulled toward the left. When the velocity control cable is pulled toward the left, the print cam follower roller is positioned under the low velocity lobe of the print cam. All further discussion of the output of this mechanism is covered in Training Program 10.4a. Let us now look inside the keyboard and engage in a bit of manipulative activity. Please follow along and repeat our steps on your typewriter. The disassembly process we will perform is frequently called butterflying the keyboard. It is carried out whenever, for one reason or another, you have to remove an interposer. Underneath the keytops, the machine comes equipped with a foam plastic dust shield, which we must lift as shown in order to locate the indicated spring. This spring holds up the repeat stop bail. As our first step, let us remove this spring. Next, we unhook the indicated restoring spring, also called the spacebar return spring. By rotating the repeat stop plate top to the front, as shown, it becomes possible to extract it from the machine by first sliding it slightly toward the left. To bring about the near vertical movement of the spacebar, it comes equipped with this guide. Remove the spacebar guide clip, as shown here, provided that your machine has the same level of spacebar guide. Do not attempt to remove the guide if the step would require breaking any adjustment. Let us first go to the next view. It should then be possible for you to remove the spacebar without disturbing any adjustment. In this example, we do not have a spacebar guide clip. Here we only need to free the spacebar shaft so that we can slide it sideways and thus disengage the indicated link from the anchor stud. Follow whatever procedure you need in order to disconnect the spacebar guide on your machine. Now loosen the nut which locks the spacebar pivot screw, and then back off the screw until it is possible to remove the spacebar and its pivot shaft completely from the typewriter. Certain chemicals used for cleaning machines have the dubious distinction of causing the foam plastic dust shield underneath the keyboard to become hard and brittle. When this happens, it is necessary to remove it, since it interferes with the operation of the keylevers. Preventing the shield from exposure to cleaning chemicals is probably the easiest solution, but not always an acceptable one. If you absolutely must submerge the whole machine for a cleaning procedure, one alternative is to remove the shield and then leave it out of the machine completely. If, however, you decide to replace the shield, you must be careful not to break the keytops while you remove them. Here you see the proper way of doing it when you have only your standard tools. IBM will sell you a keytop puller specially designed for this purpose, which does an excellent job. If you use your screwdriver and pliers only, you should alternate the sides to which you apply screwdriver pressure in order to keep any sideways strain on the keylever fitting to a minimum. You do not need to remove all the keytops. We do it here only to improve visibility during the demonstration. In your case, you need to remove only the key tops which have been left out in this frame. Go ahead and remove your key tops now. Next, disconnect the spring indicated by the red pencil from its anchor spot on the margin rack support plate. Simply leave the front end of the spring connected to the margin release shaft. Now, first we disconnect the carrier return disengagement link indicated by the green pencil. After that, all we have left to do in order to remove the margin rack is to extract the 2 mounting screws for the bracket which holds the margin rack. When you remove the margin rack from your machine, be sure to safely store the compression spring, which you will find at the left end of the margin rack. The next item on our agenda is the removal of the bell ringer bail. First, we must disconnect one end of the bell ringer bail, restoring spring indicated by the blue pencil. Then, we loosen the screw indicated by the red pencil. This will enable us to slide the bell ringer bail toward the right and thus remove it from the right side keyboard frame. When you remove the bell ringer bail at the right side, be sure not to lose the bearing washer indicated by the green pencil. The whole procedure might once again be considerably different or simpler if you happen to be working on an older style or even an 11-inch machine. In this case, you do not even have to worry about the margin rack return spring. The leaf spring indicated by the red pencil takes the place of the compression spring existing on newer machines. We leave it up to your common sense to cope with these variations in design. Now locate this keylever upstop on your machine. It consists of a steel rod covered with rubber in order to dampen the return stop of the keylevers. We shall remove it next. Unfortunately, however, there are many times when the rubber is completely dry and stuck on the brackets or clamps which support it. The most practical way to loosen up the keylever upstop rod is to apply oil to it all across the width of the keyboard. Once this has been done, it becomes rather simple to extract the rod through one of the openings in the keyboard side frame. In order to show you a few things on the keyboard, we have removed all the keytops, as you can see, and we have left half of the keylever upstop rod in position. Green pointer. We shall proceed by pivoting the keylever's top to the rear, and we have made sure that we are in a position to lift all the keylevers which use the right keylever pawl restoring spring. Notice the point indicated by the yellow pencil, which marks the separation point between the 2 keylever pawl restoring springs. If we simply went ahead and lifted the keylevers one at a time, we would strain or possibly even break the spring. Be sure to examine how the spring is held in position by disconnecting a few of its leaves and then reinstalling them again. In order to butterfly the keyboard, or to lift the keylevers without having to remove the keylever pawl restoring springs, yellow pencil, we simply used a long tool and placed it under the keylevers, as shown. You may need something a bit longer, a long screwdriver perhaps, in order to simultaneously lift up all of the keylevers on your typewriter. None of this is needed, of course, if your typewriter has the old-style keylever pawl restoring springs. Go ahead and butterfly the keylevers on your machine now. With the keylevers out of the way, we are in a position to take a close look at some of the things which we studied earlier through the use of drawings. Notice, for instance, that if we ever wanted to replace a keylever, after having disassembled the machine to this point, all we have to do is extract one more fulcrum wire. An examination of the fulcrum wire will reveal that there is only a clip, or retainer, which holds the fulcrum wire in place. The lug of the interposer, indicated by the green pencil, is pressed downward by the keylever pawl. The filter shaft will then push the interposer toward the front, disengaging it from the keylever pawl while it performs the latch selection. Later in the cycle, when the interposer is no longer held by the interposer latch spring, it is restored in a movement which is simultaneously upward and rearward. This is accomplished by the action of the now clearly visible interposer restoring springs. As a result, the keylever pawl is rotated rearward against the action of the keylever pawl restoring spring. Yellow pencil. The lug indicated by the green pencil is the repeat lug used for the underscore keylever. When the underscore key is depressed all the way down into its repeat position, the lug indicated by the green pencil does not allow the interposer restoring spring, yellow pencil, to bring the interposer back up. The repeat lug, by preventing the upward motion of the interposer, also prevents the disengagement, or the restoring, of the cycle clutch. Since the cycle clutch latch fails to reset into its rest position, the print operation is repeated for as long as the keylever is kept depressed all the way down. Be sure to notice that the repeat lug is kept well lubricated. And notice also the somewhat stronger and longer spring needed for the restoring of the repeat key interposer. Let us now remove some of the interposer restoring springs, starting with the spring to the left of the indicated underscore interposer restoring spring, and then removing all 4 of the interposer restoring springs located to the right of it. Removal of the springs enables us to examine the screws which support the compensator tube. The red pencil points at a slot through which one of the steel balls of the compensator tube is barely visible. The blue pencil indicates one of a total of 4 screws which hold the compensator tube assembly in position, together with the rear interposer guide cone. If you take a close look at the rear portion of the interposer, you will notice that the bottom of the compensator tube serves as the upstop for the interposers when they are at rest. Since these screws are used for the adjustment of the height of the interposers, this is the most important adjustment of the keyboard. As a matter of fact, it is the fundamental adjustment of the input section. The yellow pencil indicates the tail end of the screw and the nut which hold the compensator tube assembly together. We should never attempt to loosen this nut, unless we happen to want to separate the compensator tube from the rear interposer guide cone. The head of the screw whose nut we saw a moment ago is visible here, holding the clamp which ties together the tube, the cone, and the protective shield. As you can see, there are 4 of these screws in the compensator tube assembly. The only way we can gain access to these screw heads in order to retighten them is by completely removing the compensator tube assembly from the typewriter, as was done here. Notice also that the parts of the compensator tube assembly are not made of particularly strong or thick metal. It is important to mention that, when we wish to adjust the height of the compensator tube to establish the rest position of the character interposers, we should always loosen all of its support screws to the point at which it becomes possible to change the position of the assembly without much effort. Never try to tap the assembly for any reason, since it can easily be deformed and thus create a bind during the operation of the keyboard. The operator will then complain and call for your service, but when you get to the typewriter, the bind may never occur again, no matter how long you test. The same is true for cases in which dirt, such as eraser residue, has become lodged in the compensator tube. Be sure to think of this when you blow out a machine with your air compressor. This is the fundamental adjustment of the keyboard. It must always be checked before any other adjustment of the character keyboard, because it affects almost all the other adjustments. The distance between the highest spot of one of the lobes of the filter shaft and the bottom rear corner of a character interposer at rest must be 1/4 of 1 millimeter. Now that the keyboard is all opened up, it is the best time to check and make the adjustment of the height of the compensator tube, since the mounting screws can easily be reached. Check this fundamental adjustment on your machine before continuing. Don't pay much attention to the title given to this adjustment. It is just plain wrong. While the rear interposer guide comb will come along for the ride in this adjustment, it is the height of the compensator tube which is critical and which establishes the rest position of the interposers. Let us now remove a couple of interposers. First, we must remove the indicated retainer or clip. Now use a small screwdriver or any other follow-up wire to push out the interposer pivot and guide shaft until you reach the same position depicted in this frame. Then pull out the screwdriver or the follow-up wire until you clear the indicated interposer plus the interposer located to the right of it. Then pull out the 2 interposers. Finally, we have a chance to examine an interposer in our hand. Notice that they are numbered. The indicated lug positions itself between the steel balls of the compensator tube when the interposer is depressed and latched down. The _- interposer in the foreground, with a spring still on it, has only one lug pointing downward beside the wide center lug. It turns out that this lug is the one not used on American keyboards, so it doesn't matter whether it's there or not. American machines do not even have a selector bail for it. This seems to indicate that the underscore interposer does not filter out any latches when it moves toward the front. It turns out that the underscore hyphen interposer allows all the selector latches, which control the rotation of the element, to remain at their rest position. And as a result, all positive selector latches are pulled down during the cycle. Whenever the cycle clutch is made to operate without prior depression of an interposer, the machine will go through exactly the same process as far as the rotation of the element is concerned. As we examine the cavity which was occupied by the removed interposers, we can easily see the selector bail's red pencil, which during reassembly must be placed in front of the lugs of the interposers, provided that the interposers have lugs, of course. Upon further examination, we discover that the forward motion of the removed interposers would rotate the lug of the low-velocity vane top toward the front. We conclude, therefore, that even if there aren't any lugs under the underscore interposer to filter out selector latches having to do with tilt and rotate, there is one latch which will be selected, namely the low-velocity selector latch. By using low velocity to print underscores, the machine prevents the cutting of the paper. We mentioned a while earlier that the underscore, or the hyphen, would be printed if the typewriter were allowed to cycle through a printing operation without the depression of some interposer. This problem is known as flicking. There is one giveaway mark on this problem which distinguishes it from normal underscore or hyphen printing operations. During flicking, the underscore or hyphen is printed without the low-velocity selection it has during normal operations. Thus, whenever you have an occasional heavy underscore on your typewriter, you already know what's happening. The cycle clutch fails to disengage or engages without the command received from some depressed interposer. Later on in this program, we will see why this happens. Now let us reinstall the interposers and then fold down the keyboard. The keylevers are easily reinstalled by using a long screwdriver to lower the keylever restoring springs, as shown here. Once the keylever restoring springs are held out of the way, we only need to align the keylevers with their respective slots, and then reinsert the rubber-covered keylever upstop. When you're finished with this reassembly of the whole keyboard, we shall start with the keyboard adjustments. Take the time now to complete the reassembly of the keyboard. As said many times in this program, the first adjustment for the keyboard of the IBM Selectric Typewriter is the height of the compensator tube. We want 1/4 of a millimeter between the high point of the cam on the filter shaft and the lower rear corner of the interposer when the interposer is at rest. In order to enable us to check this clearance, it is necessary that we barely start the printing operation so that the filter shaft is rotated into the illustrated position. Later on, we will adjust the clearance between the steel balls of the compensator tube. At this point, however, you only need to adjust the position of the tube. Our second adjustment is that of the height and the lateral position of the interposer latch springs. Quite clearly, after having been centered in relation to the interposers, the ends of the springs should be flush with the bottom edge of the interposers when the interposers are at rest. These are the screws which hold the interposer latch springs in position. The interposer latch springs also come in 2 sections, each covering half of the total number of interposers on the keyboard. As mentioned before, the best way to observe the interposer latch springs is by tilting the machine approximately 120 degrees top to the rear, and then observing the rear of the keyboard. They cannot be seen from above because of the protective shield which completely covers them. From this angle, however, you can readily see whether or not the interposer latch springs are flush with the bottom edge of the interposers, and also whether or not they are centered with respect to the interposers. Be sure to check the adjustment at the center right and the center left, as well as the extreme right and extreme left because of the 2 sections of springs. Take whatever time you need to carry out this assignment. Once we have adjusted the position of the interposer latch springs, we can adjust the vertical position of the keeper. When an interposer is latched down by its interposer latch spring, the cycle bail indicated by the yellow pencil is also held down, and the cycle bail in turn holds down the cycle clutch latch pawl. The position of the cycle clutch latch pawl, when it is held down, is our fixed point for the adjustment of the vertical position of the cycle clutch latch keeper. We want the keeper positioned in such a manner that there is minimum clearance between the cycle clutch latch pawl and the keeper at the point indicated by the red pencil. For the time being, use an interposer located somewhat in the center of the keyboard. We will see the reason for this a little later. These are the adjustment screws, which we use to change the vertical position of the keeper. Make sure that your typewriter meets the conditions called for by this specification. After you have finished your adjustment, cycle the machine through until it is back to its rest position. Through an opening in the right side frame of the keyboard, we can observe the amount of bite which exists between the cycle clutch latch pawl and the cycle clutch keeper. The vertical position of the pawl at the yellow pencil should be such that the cycle clutch latch pawl engages, or covers, half the thickness of the metal of the cycle clutch keeper. Be sure to learn how to observe this clearance on your machine and decide whether or not it needs adjusting. As soon as you are done, we will show you how to perform the adjustment. We must also be sure to properly lubricate this point of the cycle clutch mechanism. When we make the adjustment, we must be careful not to be too skimpy, because if we are, our machine is subject to flicking. We adjust the rest position of the cycle clutch bail by means of the cycle clutch bail up stop, shown by the red pencil. Since the bail controls the rest position of the cycle clutch latch pawl, we are in effect adjusting the bite of the pawl. The green and the yellow pointers indicate the screws which hold the upstop in position. Let us insert a short note at this point. If you should notice that the cycle bail is not parallel to the wide center lug on the interposers, it may be necessary to adjust it first, by changing the vertical position of one of its supporting plates, before we advance too far with the other adjustments. Make it a habit to use interposers located in the center of the keyboard while performing these tests, and you will minimize the side effects of any lack of parallelism in the bails. You will notice that the indicated screws point in opposite directions. Both screws are threaded into the support frame. To the right of the support frame, next to the green pointer, we see the bottom end of the cycle bail up stop, whose position we want to adjust. However, we do not want to disturb the adjustment of the plate which holds the character interrupter, next to the yellow pointer. Keep in mind that we only want to move the plate indicated by the red pencil. Our first step is to loosen the nut of the screw indicated by the green pencil. As the second step, we retighten the screw indicated by the green pencil, because eventually we want this screw to keep holding the character interrupter plate while the other screw and the nuts are loose. Third, we loosen the nut indicated by the yellow pencil, which holds that screw in place. Now we are able to adjust the position of the cycle bail up stop, at the red pencil. This also changes the rest position of the cycle clutch latch pawl, and thereby adjusts the cycle clutch latch pawl bite. While we tighten the screw and the nuts, we must make sure that we do not inadvertently loosen the screw indicated by the green pencil, or we will lose the adjustment of the character interrupter support plate. You may find it worthwhile to review this sequence again. It contains the steps we must follow for the cycle clutch latch pawl bite adjustment. Remember that the condition of this bite may be one of the causes of flicking. Now make sure that your machine meets the specifications shown in this adjustment frame before continuing. Using the previously established rest position and the latch down position of the interposers, notice that thus far we have only made adjustments underneath the character interposers. Now we use the same fundamental adjustment of the rest position of the character interposers as our reference point for the adjustment of the keylever up stop, which we removed a bit earlier. At first sight, this adjustment appears rather simple and final, but not so. Notice the red numbers in the bottom left corner of this adjustment frame. Each of these numbers represents an additional keyboard adjustment, which must be checked every time we change the position of the keylever up stop. Notice that we should have approximately 0.5 millimeter of clearance between the keylever pawl and the upper lug of the interposer. This clearance is needed to allow the resetting of the keylever pawl in an operation in which the operator has held the key depressed throughout the cycle. When we start out, we must position the up stop so that the majority of the keylevers meet this 0.5 millimeter clearance. If any individual keylevers fail to meet the condition of the average keylevers, we must form them using the horseshoe forming adjustment located just to the rear of the upper lug of the interposer. The keytop is then placed back on top of the key stem. These are 2 of the 4 screws which hold the keylever guide comb and the keylever upstop in position. All 4 screws can easily be reached from the angle shown. At this time, you should perform the described adjustment of 0.5 mm distance between the keylever pawl and the upper lug of the interposers. We equalize the keylever pawl adjustment by individually adjusting those keylevers, which are too far off from 0.5 mm. Notice that we have placed the thick screwdriver shank between the ends of the horseshoe, which is being closed. This screwdriver will prevent inadvertent excess forming action on the horseshoe, which could very easily happen without the screwdriver limiting the amount of bending. Using the screwdriver will enable you to control the amount of forming you do on the keylever. Do not attempt to close the horseshoe without using some tool to limit the amount of bending. When we close the horseshoe adjustment, we decrease the clearance between the keylever pawls and the interposer lug. Now let us focus on the non-character print keylevers, called operational keylevers, which were also affected by the repositioning of the keylever upstop. Let us proceed from right to left. As we examine all of the operational keylevers located between the side frames of the keyboard, we notice immediately that the index key and the margin release key are the only keys on the inside which were not affected by the adjustment of the keylever upstop. Of these, the margin release key is strictly a manual function, whereas the index key triggers an operational interposer and engages a clutch. Notice also that the index keylever is the only operational keylever which does not have a horseshoe feature for the keylever pawl clearance adjustment. We simply conclude that the vertical position of the index keylever pawl is not adjustable. As a result, instead of adjusting the keylever pawl in relation to the interposer, we very simply adjust the position of the interposer in relation to this one keylever pawl. In your machine, locate the indicated operational interposer, latch plate, and observe that its vertical position is adjustable. This means that this operational interposer, latch plate, not only holds the position of the interposers front to rear when the interposers are at rest, but also controls the vertical position of the front end of the operational interposers. The clearance at the indicated point between the index keylever pawl and the interposer should be approximately 0.89 mm. We change the vertical position of the interposer latch plate, and thus of all of the operational interposers, by loosening the screws which hold the plate. The vertical position of all of the other operational keylever pawls is adjustable by either a horseshoe adjustment or an eccentric, depending on the level of the machine. The clearance between the operational interposers and the keylever pawls for the backspace and for the carrier return engagement mechanisms should be approximately 0.6 mm. The smallest clearance is that of the indicated spacebar keylever pawl and the spacebar interposer. It should measure only 1/4 of 1 mm. In order to obtain this improved view of the front end of the interposer, we have had to temporarily remove the right front mounting bracket from the machine. At this point, you should make all 4 of these adjustments on your machine. Finally, we have to adjust the amount of keylever pawl front-to-rear overlap with the interposers. This front-to-rear position of the keylever pawl is adjusted by forming the guide fork indicated by the yellow pencil. In older models, we might encounter adjustable screws instead of these forks, but whatever the hardware, the overlap should measure approximately 1 mm for all the keylever pawls. It is permissible to allow 1.5 mm of overlap in the case of the index keylever pawl. When we adjusted the keylever upstop, we also changed the position of the shift keylever, and we must therefore readjust its connecting linkage to the shift clutch. In order to obtain maximum transferability, we must have an ideal length for the shift keylever pawl. When we have a transfer of motion from the shift key to the shift clutch latch, or release arm, we have to position this clamp so that when the keylever has traveled halfway down, the point of connection between the clevis and the clamp is located exactly underneath the pivot point of the clamp, or simply, directly under the shift pawl. This ensures equal over-the-center travel for the clevis. Then we must adjust the length of this link by turning the indicated clevis so that the shift clutch is released or allowed to engage at about 2/3 of the downward travel of the shift key. Take whatever time you need to complete this adjustment. Our shift mechanism input adjustments are not complete until we have also adjusted the shift lock bracket, which is held in position by the 2 indicated screws. We want the shift lock adjusted so that it locks just as the clutch is released or allowed to shift into capital letters. The last key on the right-hand side of the keyboard, which was affected by the adjustment of the keylever up-stop, is the express backspace keylever. Notice that in this case we are not told to use the horseshoe adjustment. By allowing additional downward travel for the keylever after the clutch shoe has engaged with the spring, we are able to obtain the correct amount of shoe pressure on the carrier return clutch spring when the express backspace key is fully depressed. A more detailed description of this adjustment is found in our training program 10.5. On the left-hand side of the keyboard, the tab keylever was also affected by the keylever up-stop adjustment. As you trace the tabulation keylever connection to the tabulation torque bar, you will find that all of the parts, including the torque bar, are restored and held in their rest position by the indicated tab keylever restoring spring. Before we move on, note that when the keytops are removed from the key stems, it becomes extremely convenient to observe the shift lock and the shift lock bracket. Be sure to lubricate the bracket in the area where the lock slides during its operation, since this affects the touch of the keyboard. At the point indicated by the yellow pencil, we find a clevis and a link. This clevis allows us to adjust the length of the link connecting the tab keylever to an intermediate crank at the point indicated by the red pencil. After the rest position of the tab keylever has been established by the adjustment of the keylever up-stop, the link shown in the previous slide must be adjusted so that this intermediate tabulation crank does not touch the base of the power frame with the indicated arm. This arm holds the tab torque bar link. Take a moment to complete this adjustment before continuing. You will remember that on the new style tabulation lever, the J-shaped cutout, indicated by the red pencil, also provides an overthrow stop for the tabulation lever. The length of the tab torque bar link, which connects the intermediate tab crank to the tab torque bar, must be adjusted so that the torque bar has the ability to rotate the tabulation lever, at the red pencil, 1/4 of 1 millimeter beyond the latch-up point for the tabulation lever, at the yellow pencil. If you have an old-style tabulation lever, be sure to check the position of the tabulation lever overthrow plate, as was explained in Program 10.2. With this, we have concluded all of the adjustments which have to be made as a consequence of repositioning the keylever up-stop, or guide. After you have checked the tab torque bar link adjustment on your machine, we shall turn our attention to the 2 remaining keys located outside of the keyboard frame. We have seen earlier that the angular position of the tabulation stop rack is determined by the indicated tab set and clear angle. If you operate the tab set and tab clear buttons a few times, you will find that the lugs above the pencil are used to limit the motion of the tab set and clear lever. Since this mechanism is totally manual and operated from the keyboard, let us now cover it in its entirety. We have also seen that loosening the tab set and clear clamp allows us to rotate the tab rack. We must position the tabulation stop rack so that it rests the tab stops clear the tab lever pawl, as shown in this adjustment frame. This adjustment establishes the angular rest position of the tab stop rack. It is important to know that in the figure on the right, the tab stop must be rotated counterclockwise, top to the rear, all the way, before we make the adjustment. Take a moment to check it out on your machine. We have also seen before that the lateral position of the tab stop rack has to satisfy these requirements. On the left, the adjustment is for single pitch machines, and on the right, for dual pitch machines. This adjustment establishes the lateral rest position of the tab stop rack. Check it out on your machine. By loosening the indicated screw, we can adjust the position of the tab clear plate. Now let's look at the specifications. First, let us manually set a tab stop so that it becomes centered with the tab lever pawl, as shown in the top left and bottom figures. The tab clear bracket should be positioned so that a set tab stop, centered with respect to the tabulation lever pawl, clears the tip of the tab stop clear plate, also called the gang clear plate, by 1/4 to 1/2 of 1 millimeter. Notice also the adjustment of the tab set clear bracket for the snap-in type tab stop in the top center and top right figures. It requires lateral and front-to-rear positioning. In addition, keep in mind that the lateral adjustment is rather critical because dual pitch machines use only one tab rack for both modes of operation. Once all of these rest position adjustments are out of the way, we turn our attention back to the tab set and clear arms. We must now limit the amounts of throw which we obtain from the tab set and clear keylever. These are the conditions for the motion limits of the tab set and clear arms. In the top frame, we see the position a tab stop should be in when the tab stop has been set. In the bottom figures, we see the limits for the maximum tab clear action. Finally, we use the clevis indicated by the red pencil to adjust the position of the tabulation set and clear key. Notice also the yellow pencil on the key tops. It indicates the slope of the keyboard. The tab set and clear key top should follow the same slope when the machine is at rest. Again, check your machine for these requirements. For the off position of the on-off key, we follow the same criteria we used for the rest position of the tab set and clear key. The key top should be aligned with the slope of the keyboard when the switch is in its off position. But here, we have a few additional things to consider. Notice that the clevis connected to the key stem at the point indicated by the green pencil leads to the on-off switch. The yellow pencil connects the key stem to the keyboard lockout bail. The détented positions of the switch also hold the positions of the on-off key lever. Whenever we change the adjustment of the link connecting the key stem to the switch, we must also correct the length of the keyboard lockout bail link at the yellow pencil. Notice that when the switch is on, as shown here, the rear tip of the lockout bail link, at the yellow pencil, is positioned to the front of the lockout bail indicated by the blue pencil. Now let us adjust the on-off switch positions. First step, when the switch is off, the on-off key top must be aligned with the character key tops. Take a moment to perform or check these adjustments on your machine. Finally, we must adjust the angular position of the lockout bail, and for that, we start by loosening the clamp on the keyboard lockout bail. The lockout bail, at the red pencil, should be positioned so that it rests exactly under the lug on the cycle clutch latch pawl, at the yellow pencil, when the on-off switch is in the off position. This feature enables us to block the inadvertent triggering of the cycle clutch engagement when the machine is turned off. A closer examination of the lockout bail shows that it also blocks the depression of the character interposer by placing the keyboard lock lever, at the blue pencil, into the compensator tube, at the red pencil. The end result is that all of the character interposers become blocked for as long as the on-off switch is in the off position. This, of course, works only if the amount of play between the steel balls and the compensator tube has also been adjusted. And this is done by changing the position of the indicated plungers, or plugs, which exist at both ends of the compensator tube. Thus far, IBM has built 5 different styles of compensator tube plungers, or adjustment screws. No matter what the level or style of the plunger, the adjustment is the same. Only one interposer must be allowed down at any one time. When making this adjustment of the compensator tube, be careful not to force the interposers to rub against the edge of the rear interposer guide comb. Notice in the drawings that the depressed interposer is held against the right side of the slot in the interposer guide comb while the right plunger position is being adjusted. We must use the same procedure for the adjustment of the left side of the compensator tube. Among the most important adjustments of the input section, we find 2 locking mechanisms. One which prevents the shift mechanism from operating during printing cycles, shown here, and another which prevents characters from printing during shift operations. During character printing operations, the rotation of the cam follower, indicated by the red pencil, causes the lug, indicated by the yellow pencil, to interfere with the rotation of the shift ratchet, thus preventing shift clutch engagement. 2 adjustments must be made on this mechanism, the motion adjustment and the timing adjustment. On many machines, the position of the lug, at the yellow pencil, on the shift lock cam follower is adjustable. Motion, with the shift lock cam follower, at the red pencil, on the high spot of the shift lock cam, mounted onto the filter shaft, the lug indicated by the yellow pencil should just touch the bottom of the cavity between the teeth of the shift ratchet. Timing: when the machine is at rest, with the cycle shaft resting against the check pawl, the cam above the red pencil should be holding the cam follower so that there is a distance of 1 to 1.5 millimeters between the lug, indicated by the yellow pencil, and the teeth of the shift ratchet. Furthermore, the shift lock cam should hold this condition with its leading edge, so that only a small amount of turning of the filter shaft will prevent the operation of the shift clutch. While IBM calls this mechanism the shift interlock mechanism, you're much better off thinking of it as a shift lock or shift inhibit mechanism only. The word interlock is inappropriate, since this particular mechanism provides a one-way lock only. If you examine the shift cam detent, you will find that the front end of the shift cam detent operates this character interrupter mechanism, so that at the step indicated, it prevents the rearward movement of the cycle clutch latch link. Thus, the engagement of the cycle clutch is prevented for as long as the shift mechanism is in operation. There are two adjustments to consider in connection with the character interrupter. First, the front-to-rear position of the lug, and second, the angular position of the lug. When a shift operation is in progress, the indicated front-to-rear clearance between the character interrupter lug and the indicated step on the cycle clutch latch link should be maximum without allowing the engagement of the cycle clutch when the movement of the link is stopped by the character interrupter lug. The front-to-rear position of the character interrupter is controlled by the bracket indicated by the yellow pencil. Can you still remember how to adjust this bracket without changing the position of the cycle bail-up stop? First, we loosen the nut on the front screw, which is the upper screw in this picture. Then, we make sure that this screw is tight so that we can afford to loosen the rear nut and screw, at the bottom in this picture, without losing the position of the cycle bail-up stop. This enables us to change the position of the character interrupter support bracket, front to rear, into the desired position. As mentioned, the second adjustment is the angular position of the character interrupter. It is changed by loosening the set screw which holds the character interrupter lug to the support shaft. When the cycle clutch latch link has been allowed to move toward the front of the machine, the vertical clearance between the character interrupter lug and the lower edge of the cycle clutch latch link, at the point indicated by the red pencil, should be minimum. All the character interposers, with their center lug, must be able to press down in the same manner on the cycle clutch bail. To make this possible, we must align the cycle bail so that it is parallel to the center lugs of the interposers. However, the selector bails are held by the same plates which hold the cycle clutch bail in position. Therefore, when we adjust the vertical parallelism of the cycle bail to the interposers, we must simultaneously make sure that the selector bails are also positioned parallel, front to rear, with the other vertical lugs of the character interposers. These are the screws for the right bail support plate. On the inside of the keyboard frame, you can easily find the plate which holds the bails in position. When we want to adjust the parallelism of the bails, we must loosen only the screws on the right bail support plate or only the screws of the left bail support plate at any one time. Once a plate is loose, we make both parallelism adjustments. For vertical parallelism, we use the cycle bail and the center lug on the interposers to evaluate it. For horizontal parallelism, we use the selector bails and the selection lugs on the character interposers to guide us during the adjustment. Take a moment now to adjust the vertical and horizontal parallelism of the cycle clutch bail and the selector bails. One very frequent complaint with the Selectric typewriters is that they produce a lot of noise during their operation. Keyboard noise can be substantially reduced through the application of a film of grease along the full length of the character selector bails. However, do not apply this film of grease along the cycle bails. Always be sure to apply lubricant to the pivot points of the bails at the indicated points. On older machines, you will find this cycle bail damper installed on the right and left sides of the cycle bail. The objective of this device is to prevent the cycle bail from bouncing at the end of a print cycle after it has returned to its rest position against the cycle bail up stop. New machines no longer come equipped with this cycle bail damper. It is important that the cycle bail return to rest without bouncing, because bouncing could cause an uncalled-for cycle of the printing mechanism without the previous depression of a character interposer. When the shift mechanism is set to select small characters, the result of this malfunction is the printing of a hyphen. When the shift mechanism is set to select capital characters, the result is an unwanted underscore. Any uncalled-for printing of the hyphen or underscore is called flicking. If you said loosen the front one first, you are on track. Loosen the nut on the front screw, make sure that screw itself stays tight, and then you can safely loosen the rear nut and screw without losing the cycle bail up-stop position. That frees the character interrupter support bracket to move front to rear. As seen, the purpose of the selector bails is to pull a latch interposer, and ultimately a selector latch, toward the front of the machine or away from the latch bail. Older machines have a rest position for the latch links, established either by a bracket fastened to the rear of the keyboard or by a hook on the latch interposer itself. The objective of the hook is to limit the rearward travel of the latch interposer by stopping against the front interposer guide bracket. New machines have the selector bails resting directly against the vertical lug of the interposers. At this point, investigate your machine to find the device which establishes the front-to-rear position of the selector latches. On older machines, we must keep lost motion to a minimum by minimizing the distance between the vertical lugs of the latch interposers and the bails. To do this, we simply form the lugs which provide the individual rest position stops for the latch interposers. Finally, we want to position the selector latch fully under the latch bail when the latch is at rest. Maximum overlap, or rather underlap, beyond the rear vertical edge of the bail should be 1/4 of 1 millimeter. On late-style latch bails, or cam followers, the rearward motion of the selector latches is limited by the indicated plate. This plate is positioned immediately to the rear of the latch bail or cam follower. No matter what style of latch bail your machine has, we want full engagement of the selector latch under the indicated latch bail or cam follower. When we have a plate to the rear of the latch bail, we must be careful not to have any loss of motion between the latch interposer link and the selector latch. The length of the latch links can be adjusted by these clevises. These links control the front-to-rear rest position of the selector latches on older machines. On newer machines, which come equipped with a back plate on the latch bail or cam follower, they control the amount of lost horizontal motion which may exist during the latch selection process. Now check your machine for full latch engagement with the positive latch bail if your machine is a newer model, or 0.25 mm underlap of the selector latches with a positive latch bail if it is an older one. Be sure to also check for minimum loss of motion if your machine is a recent model. Similarly, adjust the link which controls the 0.5 rotate bail so that you have approximately 1.5 mm overlap between the selector latch and the adjustment screw on the 0.5 bail. Take a moment to check the 0.5 selector latch overlap on your machine. If we wanted to complete all latch adjustments having to do with character printing, we would now turn to the low-velocity selector latch. However, to continue proceeding from left to right in the machine, we shall leave the low-velocity selector latch adjustment for later. The operational latches should be positioned horizontally so that, at rest, they clear the bail of the cam follower by approximately 1/4 of 1 millimeter, as shown. The adjustment is performed by allowing the rear of the interposer to come down when we want to increase the clearance between the latch and the cam follower, and by raising the rear of the interposer when we want to decrease this clearance. These are the screws which control the horizontal front-to-rear adjustment of the operational selector latches. They are located underneath the operational cage. Actually, these screws control the vertical rest position of the rear of the operational interposers. And due to the angle and the shape of the operational selector latches, the height of the rear portion of the interposers ends up controlling the horizontal front-to-rear position of the corresponding latch. Since there isn't any index selector latch, we simply adjust the rightmost screw to match the others. In fact, on dual pitch machines, the spacebar mechanism doesn't have a selector latch either. This is why the same criteria applies. Have the adjustment screw for the spacebar interposer match the screws located in the center of the operational cage. Finally, we adjust the position of the low-velocity selector latch. The link indicated by the yellow pencil must be adjusted so that the low-velocity selector latch, at the point indicated by the red pencil, is flush with the bottom surface of the cam follower when the mechanism is at rest. Check that your machine meets this condition. Notice also that the low-velocity mechanism restoring cam has 2 scribe marks on it. At rest, the cam should be positioned so that the first scribe mark on the cam, below the green pencil, is aligned with the mark on the cam follower. You can easily check your adjustment of the length of the link. During the printing operation of a low-velocity character, when the second scribe mark on the cam, above and to the rear of the green pencil, is aligned with the mark on the cam follower, the low-velocity selector latch should clear the lug on the tail of the cam follower by 0.25 millimeters. The front-to-rear clearance between the low-velocity selector latch and the cam follower, at the point indicated by the green pencil, is also adjustable. Notice that this low-velocity mechanism cam follower is made up of 2 parts, one which rests on the cam, at the yellow pencil, and the other, to which the low-velocity mechanism drive spring, at the red pencil, is connected. The 2 parts are held together by the rather large adjustment screw directly under the pivot point of the cam follower. When the whole mechanism is at rest, as shown, the front-to-rear clearance between the selector latch and the cam follower at the point indicated by the green pencil should be approximately 1/4 of 1 millimeter. If this clearance is too large, the cam follower may rotate too much during high-velocity character printing operations, pulling on the velocity control cable, at the blue pencil, during cycles in which the cable should be left undisturbed. On the other hand, if we do not allow for this clearance, we may print some or all of the characters at low printing velocity. The operational interposers are restored by the bail indicated by the red pencil. The bail is rotated directly by the operational cam followers when they act on either one of the 2 lugs on the sides of the bail, at the blue pencil. We must be sure to restore the interposers toward the front of the machine so that they are pushed anywhere from 1/4 to 3/4 of 1 millimeter beyond the latch-up point with the operational interposer latch-up plate located above the front end of the interposers. Form the lugs, at the blue pencil, bringing them closer to or further away from the pivot point of the restoring bail in order to respectively increase or decrease the output motion of the bail. On very old machines, you might add flat clips to the shaft or beam of the restoring bail when you need to shift the bail motion further to the front of the machine. Be sure to check this 1/4 millimeter clearance on all the operational interposers of your machine. Test the restoring interposer action, making sure that in the process you try both lugs of the restoring bail. If you haven't already done so, let us now reinstall the margin rack. Be sure to reconnect the carrier return mechanism disengagement link indicated by the green pencil. The length of this carrier return mechanism disengagement link should be adjusted to establish the indicated clearances when the rack is held all the way to the left. Take a moment to check this on your machine. The angular rest position of the margin rack is adjustable in different ways on different models, as you can readily verify in the adjustment and parts manual. The rack should always be in a horizontal position when the machine is at rest, however. In this case, the angular rest position is adjusted by forming the lug on the extreme left of the margin rack, called the margin set lever stop by IBM. Once the margin rack has been installed, we also reinstall the bell ringer bail. The rotation of the bell ringer bail is controlled by the bell ringer bell crank, shown in blue in this frame. When the carrier moves into the right margin, the first step of the line lock bracket rotates the bell crank and the bail so as to ring the bell and alert the operator. With a second step on the line lock bracket, the keyboard lockout lever, or dummy interposer, is pressed down into the compensator tube so as to lock out the character keys on the keyboard once the carrier reaches the right-hand margin. The bell is rung by the action of the bell bail lever, at the green pencil, onto the bell hammer. By loosening the screw indicated by the red pencil, it is possible to change the lateral and angular position of the bail lever. Notice that the bell ringer bail is kept rotated top to the rear by the action of the spring indicated by the blue pencil. As mentioned earlier, we adjust the angular position of the bail lever so that it acts on the indicated spring, pushing it down and eventually releasing it to allow the ringing of the bell. All of this must be accomplished with the motion obtained from the first step of the line lock bracket, which is transmitted to the bell ringer bail. Be sure that the bail lever is also properly restored above the indicated spring when the bell ringer bail is allowed to return to rest, and finally, that the bail has enough end play to operate freely. Take the time to check all of this now. With the additional top to front rotation of the bell ringer bail resulting from the second step on the line lock bracket, when the carrier reaches the right margin, at the red pencil, and through the lever fastened at the point indicated by the yellow pencil, the line lock mechanism locks the keyboard. Form the lever fastened to the bell ringer bail until it completely depresses the dummy end. Then insert the interposer into the compensator tube. Finally, depress the margin release key so that the bell ringer bail returns to its rest position. With the pressure retainers on the indicated pivot point for the spacebar, it is possible to limit the sideways play of the spacebar. The final position of the spacebar must of course be checked with the central section of the machine case in position. Before you reinstall the case, be sure to check whether all the keylever pawl springs are properly installed and that all the pawls are correctly positioned. The lugs, of which one is indicated by the yellow pencil, belong in the cutout shown by the red pencil. Try to operate each character key at least twice before you allow it to pass your final inspection. The reason for this is that some of the keylever restoring springs might not be under the keylever, and this would cause the key to become inoperative after the first depression. Now we turn to the very bottom of the keyboard. First, let us investigate how the repeat stop plate operates, and then you may check your machine for the correct conditions. With the exception of the carrier return interposer, the operational interposers can be made to continuously repeat their operation through maximum depression of the keylevers. In the upper left corner of this frame, we find a keylever pawl and an interposer at rest. Be sure to notice the amount of front-to-rear overlap existing between the keylever pawl and the front tip of the interposer. This overlap should be anywhere from 1 to 1.5 millimeters. It is adjustable by forming the guide plate, which holds the keylever pawl, and which in this drawing is erroneously labeled interposer latch plate. At the bottom left, we see the position of the parts after the keylever has been depressed until it stopped against the repeat stop plate. Evidently, this releases the interposer. When the keylever is held depressed in this position throughout the operation, we find that at the end of the operation, the parts assume the position depicted in the upper right corner of this drawing. Notice that the keylever pawl was deflected towards the front by the returning interposer. Furthermore, the returning interposer was also allowed to relatch with the interposer latch plate. But notice also that the repeat lug of the keylever pawl is positioned just above the front tip of the interposer. It is important that the repeat stop plate stop the keylever at the proper height, just after the interposer is released, as in the figure at the bottom left. If, however, we continue to depress the keylever, thus forcing the repeat stop plate to rotate also, we arrive at the condition shown in the figure in the lower right corner. Before we move on, examine the carrier return keylever pawl on your machine, and you will find that we can only obtain one carrier return operation per key depression. If we depress the carrier return key all the way into the repeat position, we obtain repeat indexing because of a specially shaped repeat lug attached to the carrier return keylever pawl. At this point, if you haven't already done so, finish off the reassembly of the keyboard on your machine by reinstalling the repeat stop plate. Notice that the indicated spring holds the repeat stop plate rotated upwards. The action of the spring is limited by the lug, which partially covers the tip of the pencil. This lug rests against the bottom of the right side frame of the keyboard. By forming this lug, we should position the repeat stop plate so that it is in the way of the keylevers just as the interposer is released during single operations. In conclusion, notice that the space bar mechanism uses a separate lug on the repeat stop plate. It should be adjusted last. As a final point, we ask you to think of the input section of the IBM Selectric Typewriter as being represented by all of the mechanisms which have to do with the horizontal front to rear movement of the selector latches, and those mechanisms which allow the engagement of the keyboard. The movement of selector latches constitutes the selection process, and the engagement of some clutch is merely a form of power tapping which the typewriter uses in order to electrically drive the selected mechanism. What happens after this point is part of the output section of the machine. Thus, you can easily see that the name Selectric is an extremely well-conceived name for this machine. Ideally, the operator goes only to the keyboard to make the machine operate. The most important part, which acts as a go-between for the keyboard and the output function, is the Interposer, another well-conceived name for a part. With this, we conclude the training program on the input section of the IBM Selectric Typewriter. We suggest that you continue with program number 10.4 on the output section of the Selectric Typewriter. Thank you for the time you have devoted to this program.